in a new fireplace, so it's definitely time to focus on conic sections. What's the relevance? Well, in Latin, focus is fireplace, and all conic sections have a fireplace of their own. So I've thrown a diagram of the conic sections we'll cover. First off, circles! Now, the circle is the collection of all points that are equidistant to a single point, or the focus. In this case, let us name the focus Big F. And let's put on some axes. Remember to label your axes, otherwise people go mad. Now, this is X and this is Y. Y, it's convention, stick with it. If we were to choose any point, anywhere on the line, or on the circle in this case, we have this point. We could draw a line from the origin to the point, and we could decompose it into its vertical and horizontal components. And Pythagoras will have you covered. If we name the hypotenuse A, then A squared will be given as x squared plus y squared. This could also be written as A is equal to the square root x squared plus y squared. And that's pretty much our circle covered. For a second conic section, we have the parabola, and since they're a bit time consuming to draw properly, you saw the diagram, I will just do a rough outline. You can look up Steiner constructions if you need a more precise drawing. So we have the focus, and let's just name the focal length small f. Then the directrix, we'll draw it in yellow. It's supposed to be F down from the x-axis. And it's supposed to be going parallel to the x-axis. Now, if we were to choose some point along the parabola, let's say here, and then by the definition of a parabola, if we name this distance d, then so must this distance be d as well. Because it's all the points, it's the collection of all the points that are equidistant from a single point to a line. This one is named small f as well. Now from, we're also going to draw another line. Let's do that one in yellow as well. So the point, if parallel to the x-axis, the point that so this line that goes from the focus parallel to the x-axis, when it hits the vertex, you have this semi-latus rectum. Grow up. Nah, I'm just joking. If we were to continue this all the way to this point where it intersects D, well, we could make the assertion that y is equal. So we take this distance is y, we subtract f, we get this distance. And since we know this is how far we travel along the x direction, we know that d squared must be equal to x squared plus y minus f squared. Further on, we know that this distance, so this d, well, it must be equal to y plus f. So we can also say that d is equal to y plus f. We want these two to be on the same form, so we square this thing, and we need to square the other side as well. Now we have the same d squared, then we can set this thing equal to that thing. And so we have x squared plus y minus f squared is equal to y plus f squared. We're just going to expand, so we're expanding this. So we have the x squared, and we're expanding this term, so we have y squared minus 2yf plus f squared. And then we have this thing, so this thing is equal to, we're expanding this one, so we have y squared plus 2yf plus f squared. Now take note that we have some similar terms. We have an f squared and an f squared. So we're subtracting f squared from both sides. And we have y squared and y squared, so we're subtracting y squared from both sides. This was supposed to be a plus y squared, but it will be there no more. So we're left with minus 2yf plus 2yf. Let's just add this. Let's just add 2yf to both sides. Then this one will cancel. We already have one here, so this 2 simply becomes 4. And the plus is sort of redundant. We know that it's positive. So we have x squared is equal to 4yf. We would like maybe to have the y by itself. So we could say that y is equal, so we're dividing x by 4f. So we have x squared divided by 4f. And here we have the equation for a parabola. Next up, we have a third conic section, and the first one with 2 foci, not one focus, 2 foci. The ellipse! And now, I know what you're thinking, but Jay, you only have one fireplace. What could you potentially know about the intricacies of a conic section with 2 fireplaces? Well, if we just follow around my hallway into the petty excuse I have for a bathroom, ignore all the junk. If we just have a look down here, we see my toilet. But that's besides the point. What do we have here? If it isn't a bathroom fireplace. And now, depending on my eccentricity, which is simply a measure of how much a conic section deviates from a circle, look at the illustration, I'm either a hyperbola or an ellipse. Let's go to the blackboard and find out. So we're back at the blackboard, and unless you've been living on an internet rock the past few years, you've probably seen this thing before. It's an ellipsing tool. I've taken a piece of wood, I've attached 2 screws in it, and I have a piece of string tied to a loop. That way, the distance from the chalk to the 2 screws will also always be a constant, and that's also the definition of an ellipse. So let's just... we have drawn an ellipse. Next we just find a point somewhere in the ellipse, and we will name this distance d1, this distance d2, and we will also, so we move our point up to the top. Take note that when we're at the top, D1 is equal to D2. So let's just name one of these. Well, they're both the same, so we'll name it A. Then we can state that 2A is equal to D1 plus D2. Further on, we're going to name the distance from the origin. It's going to be C. So if we were to imagine that we shift this thing over like that, it would be the ordinary circle equation for this right angle triangle. but since we're starting from this point and going out, then d1 squared is equal to x minus c squared plus y squared, and d2 squared is equal to x plus c squared plus y squared. If we now take the square root of this, both sides, then this thing becomes square root. We do the same to this one. So this becomes the square root. Then we have d1 by itself and d2. Then we can substitute into this equation. But before we move on, we're just going to make a short observation. This is a right angle triangle. And this thing is known as the semi-minor axis. We're going to label it B. So we can make a right angle triangle right here. And we can say that B squared is equal to A squared minus C squared. We just flipped around the Pythagorean identity a bit. Now let's do some working out. We have, so take note, this thing, this thing, this thing, this thing. Then we can say that 2a is equal to the square root x minus c squared plus y squared plus the square root x plus c squared plus y squared. We would like to isolate one of the square root. It doesn't really matter which one you do, but we'll subtract that one from both sides. So we get 2a minus square root of x minus c squared plus y squared is equal to the square root of x plus c squared plus y squared. Then we can take the square of both sides. So, squaring this side, we get to remove the square root from this side. And we're just going to expand this term and that term in term. So we get 4a squared minus 2, but it's 2 times 2, so we actually get 4a square root of x minus c squared plus y squared. And then this thing to itself just becomes x minus c squared plus y squared. And this whole thing is equal to that thing. We have a y squared and a y squared. So let's just remove this. We can say that this thing is equal, so this thing is equal to that thing. We have a y squared term and a y squared term. We're just going to cancel those. And we're going to expand on this one and this one. So let's just rewrite the whole thing. We have 4x squared minus 4a square root of x minus c squared plus y squared plus, so let's just do this thing, x squared plus 2xc. I've written the plus, it's supposed to be a minus. Minus 2xc plus c squared. And So it was equal to this thing. We're just going to expand. So this thing is equal to x squared plus 2xc plus c squared. Now, take note that we have a 2xc and a 2xc, we have a c squared and a c squared, and we have an x squared. So let's start by subtracting c squared from both sides. We get to cancel those. Subtract x squared from both sides. We get to cancel that one to that one. And we have this thing. So we're going to add 2xc to both sides. So we get to cancel this one. If we add 2xc to that one, we are left with 4xc. So we have 4a, 4 something something, 4 something something. Well, divide both sides by 4. We get to cancel the 4's. And let's just rewrite what we have. Or do we want to do... So, yeah, let's just do it this way. We have this a term. Let's start with that. So we have a squared. Let's just subtract this one immediately. Minus xc. And we're adding this thing to both sides. So it disappears from this side and we get a square root of x minus c squared plus y squared. Alright, let's just erase. So far, so good. If we were in the situation where we got the square root on one side, well, let's just square both sides. Then this a becomes an a squared, and this whole square root business simply becomes a parenthesis. Great, let's expand this term. So a squared by a squared becomes a to the 4th power minus, we have an a squared and this xc, so minus 2a squared xc, and then we have xc minus xc times minus xc, so we have plus x squared c squared. And that is equal to this thing. I think let's just do a short expansion down here. So this is also equal to a squared times. So we're expanding this thing. X squared minus 2xc plus c squared plus y squared. So if we move back up to this one, we know that this is equal to this. We're going to multiply in the a's immediately. So we have an a squared x squared minus a squared times 2, so we have 2a squared xc, and then we have an a squared c squared, and we have an a squared y squared. Now if we compare it to our previous term, we have this 2a squared xc minus 2 squared ac xc. Well, we'll add that to both sides. We just get to cancel that one. Pretty nice, pretty nice. And then we have let's see, we're going to rewrite the whole equation, but we're going to move the terms around a bit. We like all the constant terms on one side. So we have an a to the 4th a to the fourth, and we have a squared c squared, those are only constant terms, so we'll subtract, so we have an 8 squared c squared, and we like the x and y terms on the other side. We have this one from before, so we have an a squared x squared, and we have, so we have to subtract that one from both sides. Subtract x squared c squared, and this one is just left as it is, plus 8 squared y squared. Now, erase. So, a to the fourth, a squared, we can factor out an a squared from both of those. So we have 8 squared times a squared, so a squared becomes 8 to the fourth minus, so we factor out a squared, we have c squared. And then on this side, take note of the x squared term. So we have that this is equal to, we factor out the x squared, and we have an 8 squared minus c squared. And we're simply left with an 8 squared y squared. Now, remember, like way back, this thing, a squared minus c squared, well, a squared minus c squared, a squared minus c squared, we get to substitute. Alright, so we have a squared b squared is equal to x squared b squared plus 8 squared y squared. And wouldn't it be look super pretty if this thing was 1? So we're just gonna divide. We're gonna divide by a squared b squared. And if we do it on this side, we need to do it on this side as well. 8 squared b squared. 8 squared b squared. Oh, but lo and behold, this whole thing just cancels out and becomes a 1. Oh. We have a b squared and a b squared, so those cancel. And we have an a squared and an a squared. So those cancel as well. And now, lo and behold, we are left with our equation for an ellipse. The sum of a squared over x squared over a squared plus y squared over b squared is always equal to 1. Now, for our fourth and final conic section, because we will not be covering degenerate cases, and I'm not exaggerating, we have the hyperbola! And in the interest of keeping the video short, I will not do the derivation. I will, however, leave you with enough to work it out on your own. Let's see. So remember that a hyperbola is the collection of all points where the difference of the distance to two other points, the foci, is a constant. So let's just freehand the hyperbola right here. Now let's see. If we take some point on the hyperbola, we draw the distance d1. Let's draw the other one, d2. And imagine that we were to move this point all the way down. Then this distance and this distance, they are both the same. So we're just left with whatever remains in between. And let's call that, we will call this, so the distance from the origin to the vertex is A. And this distance we will call C. distance to the focus, we have pretty much all we need to set up our equations. So if this is A, then 2A is equal to D1 minus D2. And just as with the ellipse, we could make some kind of right angle triangle, and we shift it over, so we have that D1 is equal to the square root of x minus c squared plus y squared, and D2 is equal to the square root of x plus c squared plus y squared. And just so you have something to go on after you've done your working out, the equation should end up looking something like x squared over a squared minus y squared over b squared is equal to 1. Now, to summarize our results, we have for the circle, it had the equation x squared plus y squared is equal to a squared, and its eccentricity is 0 because it doesn't deviate from the circle. The parabola, it had the equation y is equal to x squared over 4f, and its eccentricity is 1. The ellipse, we have the equation x squared over a squared plus y squared over b squared is equal to 1, and its eccentricity, it's given by the square root of 1 minus b squared over a squared. And finally, the hyperbola, have the equation x squared over a squared minus y squared over b squared is equal to 1, and its eccentricity is given by the square root of 1 minus plus b squared over a squared. And that's our conic sections. Thanks for watching.